Hello, this is a joint probability distributions video project for statistics class. We're team 25, and here's our presentation. Next slide. What is a joint probability distribution? Joint probability is a probability of two events happening together. For example, probability of pulling a card out of a standard deck and pulling a 5 and the card being black would be 2 out of 52. Joint probability distribution shows probability of two or more variables as a table with each outcome shown. So in the table given below, for example, probability of getting a 3 and a C would be 0.1. So if the random variables are discrete, we can use joint probability mass function or a PMF. They obey same rules as regular PMF of any other random variables. They can be negative and they have to add up to to 1. Also, calculating the probability of a specific range would be the same thing as calculating each probability in the range and summing them up. Next slide. So density function. If random variables are continuous, we can use density function. They follow same exact rules. They can be negative and they have to add up to 1. And if you want to find the probability of a range of values, we can take double integral of the probability density function across the range A. Next slide. Here's a joint probability graph with marginal densities on the sides and sample observations in the middle in the green. Next slide.
Okay, so I'll be talking about types of joint probability distributions. So next slide. So first we'll have marginal probability. So marginal probability is a probability of an event irrespective of the outcomes of another variable. This occurs if all the outcomes and probabilities for two variables were displayed on a table with X as columns and Y as rows or vice versa. The marginal probability of X would result in the sum of probabilities for Y on the margin of the table. So this differs from the conditional probability as it considers the union of all events for Y rather than the probability of a single event. So as for conditional probability, it is the probability of one event occurring in the presence of a second event. It can be calculated as the conditional probability of event X given event Y being equal to the probability of event X and event Y divided by the probability of event Y. So with this calculation, it assumes that the probability of event Y is not equal to 0, as it will make the conditional probability undefined. Next slide.
So covariance and correlation allow you to talk about how two random variables are related to one another using numbers. Covariance specifically can be calculated by taking the expected value of the product of the standard deviations of X and Y. And it's positive when X and Y are positively correlated, meaning large values of X are associated with large values of Y. And then it's negative when there's a negative correlation, meaning when large values of X are correlated with small values of Y and vice versa. And if X and Y are not strongly related, then the covariance is likely to be near 0. One of the weaknesses of covariance, however, is that it can be very strongly affected by the standard deviations, which can cause difficulty in trying to determine how two variables are related. And so correlation is often used instead of covariance. And correlation is calculated by just dividing the covariance by the product of the standard deviations. And that returns a value between -1 and 1, which essentially standardizes the covariance and allows you to more easily compare the correlations of two or more variables.
Okay, and I'll be providing a real-world engineering example of joint probability distributions. Next slide. Okay, so in a particular vehicle, for example, let's say each front tire should be filled to a pressure of 27 psi, and an engineer wants to calculate the probability that both front tires are underfilled. If we represent the front tires both with variables x and y, we can actually solve this issue using joint probability distributions. Next slide. So with the given distribution and using the density function, which is again the double integral of the range and f of x and y dx dy equal to 1 when f of x and y is greater than or equal to 0, you can solve for variable k in the distribution, and from there use the formula to solve for the probability, which would be 0.4304.
So speaking of correlation and covariance, there are strengths and weaknesses to them. So when discussing joint probability, you do have to find the relationship between the two variables. This was discussed beforehand. If the covariance is negative, then that would mean that one variable would have to be greater than or less than the other variable. So for example, if I was talking about the two variables being the weight of a plane and the weight of a load on a plane affecting the success of a flight, then if the covariance was negative, then that means that one type of weight would have to be less than the other type of weight. This would make sense since we don't want something too heavy, otherwise the plane would have trouble staying in the air. So since correlation is based on covariance, correlation focuses on the linear relationship. So this means like if the load increases, then the weight would have to decrease. If the weight decreases, then the load would have to increase. The weakness of covariance would have to be the fact that if there was a wide range of results, it is hard to interpret. If we have to test the probability of successful flights with X pounds of plane weight and Y pounds of cargo weight of 1,000 planes, for example, then the covariance would be hard to interpret. And since correlation doesn't focus on outside factors, we can't take external factors such as weight distribution, weather, or even flight paths into account when calculating the probability of a successful flight only based on the two types of weight of the plane. These are our citations for the entire PowerPoint, and that concludes our statistical project on joint probability.